Okay, ladies and gentlemen, we're going to do section 8.4 today on page 392, the Ohmic region. You will recall from previous sections where we've discussed the characteristic curve of the field effect transistor, the Ohmic region. It's the portion of the field effect transistor curve in which the Ohm's law can be applied. When properly biased in the Ohmic region, a JFET exhibits properties of a variable resistance, where the value of the resistance is controlled by VGS. This is also one method of the field effect transistor being used. Alright, if we look at figure 830, you can see the Ohmic region is in the shaded area. The characteristic curves are straight lines with a slope of ID divided by VDS for small values of ID. You can see here my axis, I've got ID and I've got VDS. So for these values I can calculate values of ID. But let's see how it works. The Ohmic region extends from the origin of the characteristic curve to the breakpoint where the active region begins. We can see here from the origin up to the active regions for each of these curves. And you can see it's in a roughly parabolic shape, as shown on a typical set of curves in figure 830. The characteristic curves in this region have a relatively constant slope for small values of ID. The slope of the characteristic curve in the Ohmic region is the DC drain to source conductance of the JFET. So I can see then for the slope, GDS is ID divided by VDS. Again, so I can see my axis names. Recall that resistance is the reciprocal of conductance. So the DC drain to source resistance would then be RDS, the inverse of RDS or reciprocal, 1 over GDS, which will be VDS over 1D. ID. The JFET has a variable resistance just below figure 830. A JFET can be biased in either the active region or the Ohmic region, but of course we're discussing the Ohmic region now. JFETs are often biased in the Ohmic region for use as a voltage-controlled variable resistor. Underline that. That is the use of the JFET in this case. It can be used as a voltage-controlled variable resistor. The control voltage, of course, is VGS. Still here. You can see here on the right-hand side, VGSs. And it determines the resistance by varying the Q point. Let's have a look here on figure 831. So to bias a JFET in the Ohmic region, the DC load line must intersect the characteristic curve in the Ohmic region as is illustrated here. Here you can see they've shown it, and they've also shown it here in enlarged. Remember, we've seen the shaded areas before the active region, so the active region basically ends there. And then I can see for this specific section that it is in the Ohmic region that my load line cuts my characteristic curves. So I have Q0, Q1, and Q2. Alright, so to do this in a way that allows VGS to control RDS, the DC saturation current is set to a value much less than IDSS, so that the load line intersects most of the characteristic curves in the Ohmic region. As you can see here on figure 831. Alright, of course I won't do it up there because it's not going to work properly. So IDSS is up there, so you can see what I'm doing here. ID sat is a much lower value. So I calculate there, if you will look at the bottom of page 393, ID sat is VDD divided by RD. And if I go and look at the circuit diagram on figure 831, I can see that VDD is equal to 12 volts and RD is equal to 24 kilo ohms. The same as we have done to calculate IC sat in a BJT. Now in this case it will be 0.5 milliamps. So you can see it's much lower than IDSS over here. So then it shows that the operating region expands PQ points there where it is enlarged here, Q0, Q1, and Q2. So as you move along the load line in the ohmic region, the value of RDS varies as the Q point falls successively in curves with different slopes. The Q point is moved along the load line by varying VGS is equal to 0 to VGS is equal to -2. Now you can see there the first one is VGS is equal to 0, so that is going to intercept there, where Q0 for VGS -1, I can see it cuts my curve over there, and then for VGS2, that will be the third point there on the load line where it cuts. So as this happens, the slope of each successive curve is less than the previous one. So a decrease in slope corresponds to less ID. You can see here, it moves in that direction, so it decreases. And at the same time, what happens to VDS? It's over here. You can see as I move along from 0 to -2, that VDS increases. So this implies an increase in RDS just by using Ohm's law. R is equal to V over I, and if I decreases and V increases, then of course the resistance will also increase. Okay. Then you can also underline the last sentence there. This change in resistance can be exploited in a number of applications where voltage control of resistance is useful. All right, but let's have a look at example 814 just to make sure that we understand. Example 814 says an N-channel JFET is biased in the ohmic region as shown in figure 832. The graph shows an expanded section of the load line in the ohmic region. As VGS is varied from 0 to -3 as indicated. Here you can see VGS, there is 0, -1, -2, -3, all the points that is still in the ohmic region. Remember, the ohmic region is just below the knee where the current becomes constant for ID. And then the graph shows the following Q point. So I can see then for Q0, which is this point over here, ID is approximately 0.36, because this is 3. So it's approximately 0.36 milliamps, and VDS, in that case, if that is 0.5, then this is 0.25. And if I go down here, it's about halfway there, so it should be 0.13 volts. All right? So I can see that all these values I can get from the graph. So Q1, ID is 0.355 milliamps, VDS is 0.27. And for each of these, I can go and read the values from these curves. And therefore Q2 as well, I can go and read the values from the curve. All right, now I have to determine the range of RDS as VGS is varied from 0 volts to -3 volts. So I've got all the Q points, so I've got the values for ID and VDS. I just apply Ohm's law. If I go and look at the solution there on page 395, so Q0's RDS will be VDS over ID. I've seen the values for Q0's ID and VDS has been, we read here, 0.36 milliamps, and VDS was 0.13 volts. And I divide and I get a value of 361 ohms. And you can see as I move along that load line that the resistance increases. Now at Q1, the resistance is 760 ohms. Q2, resistance is 1.2 kilo ohms. And at Q3, 2.9 kilo ohms. So I can see that I control the value of the resistance in the ohmic region by changing the value of VGS, as I've seen here on figure 8.32. Alright, carrying on below, example 814 on page 395, Q point at the origin. In certain amplifiers, you may want to change the resistance seen by the AC signal without affecting the DC bias in order to control the gain. Right, this is explained on figure 833. So sometimes you will see a JFET used as a variable resistance in a circuit where both ID and VDS are set to 0. So how do I accomplish this? Which of course means that the Q point is the origin. This is accomplished. The Q point at the origin is achieved by using a capacitor in the drain circuit. You can underline that of the JFET. This makes the DC quantities, because we know what the capacitor does with DC. It blocks DC. This makes the DC quantities VDS is equal to 0, and ID, of course, will also then be 0 milliamps. So the only variables are VGS and ID, the AC drain current. At the origin, you have the AC drain current controlled by the VGS. As you've learned earlier, transconductance is defined as the change in drain current for a given change in gate to source voltage. Remember that formula, GM is equal to delta. Where was it? On page, let me just show you again. On page 379, GM is delta ID divided by delta VGS. Page 379. You can refer back to that. So the key factor when you bias at the origin is the transconductance, of course. So figure 833 shows the characteristic curve expanded at the origin. Notice that the ohmic region extends into the third quadrant. I can see here that the ohmic region actually extends up to here. Remember, up to below the knee of my characteristic curves. So at the origin, where VDS is equal to 0 volts and ID is equal to 0 milliamps, the formula for transconductance, which we've also seen on page 379, GM is equal to GM0. Remember, where VGS is equal to 0, is multiplied in brackets, 1 minus VGS over VGS off, close the brackets. Now, where GM is the transconductance, GMO is the transconductance for VGS is equal to 0 volts. And then GMO can be calculated from that following equation, which we've also seen on that page. GMO0 is 2 times IDSS divided by the absolute value of VGS off. But let's have a look at example 815, just to make sure that we understand what we have to do here. It says there, for the transfer characteristic curve in figure 833, calculate the AC drain to source resistance for a JFET biased at the origin if VGS is equal to minus 2 volts. Assume IDSS is 2,5 milliamps and VGS off is equal to minus 4 volts. Alright, then I just have to apply these two formulas. First, I'll have to find the transconductance where VGS is equal to 0. In other words, GM0. 2 times IDSS over absolute value of VGS off gives me a value of 1,25 millisiemens. Then I have to calculate GM at the VDS of minus 2 volts, which is going to give me a value of 0,625 millisiemens. And then just to determine the AC drain to source resistance of the JFET, of course, is just the reciprocal of the transconductance. So the reciprocal of 0,625 millisiemens is 1,6 kilo ohms. All right, that concludes section 8.4, where we discussed the ohmic region of the field effect transistor.